In the previous video, we saw how linear search works. We looked at the pseudocode of linear search and the running time analysis. And then we also saw how binary search works. How sorting the initial sequence that is given to you allows you to do searching more efficiently. So here's the pseudocode for binary search. Assume that the input is given to you in an array A of size n, and assume that the subproblem we are working with at each stage is delimited by the indices of the first and the last element in the subarray. Right? So recall from the previous video that in each step of binary search, we are going to be focusing our attention on a particular subarray of the original array. And the length of that subarray is going to go down by a factor of 2 in every iteration. So we can define that subarray by the first and the last element, by the indices of the first and the last element of the subarray. So initially, the subproblem or the problem we have is of size n. The subarray is simply 1 to n. So we're going to use a variable called lower to point to the first element of the subarray, and we're going to use a variable called upper to point to the last element or the right end of the subarray corresponding to our subproblem. So we initialize lower to be 1 and upper to be n. Now we are going to enter a loop where we will repeatedly compare v with the middle element of the subarray. So we are going to compute this index of the middle element, which you're going to store in a variable called middle, and the index is going to be given by the average of lower and upper, lower plus upper by 2. And we're going to have the ceiling operator to round up the index in case it happens to be a fraction. Now we are going to compare v with the value of the middle element, and if it turns out that v is equal to the middle element, then we're going to return the index of the middle element. So the algorithm will terminate at this point. But if v happens to be less than the middle element, then we know that we can discard the right half of the subarray we are looking at currently. And the way we are going to do that is by changing the upper limit of the subarray from here to here, because knowing that v is less than the middle element, we can restrict our search to the elements in the left half of this subarray. And to do that, we can redefine upper to be equal to the index of the rightmost element of this subarray, which is given by middle minus 1. So upper will be set to middle minus 1. Else, that is, if v is neither equal to the value of the middle element and it's neither less than the value of the middle element, we know that it must be greater than the value of the middle element. So it must be present in the right half of this subarray. And if you're going to work with the right half in the next iteration, then we have to redefine the lower end of the subarray to point to this leftmost element, whose index is going to be given by middle plus 1, because it's the element to the right of the middle element. So in this third case, where v is greater than a of middle, we are going to redefine lower to be middle plus 1. And then we'll enter this loop again. So our range is going to go down. Ultimately, we're going to end up with a subproblem of size 1. When we end up with a subproblem of size 1, both upper and lower will have the same value. And the value of the middle element is also going to be the same, because if upper and lower are the same, then upper plus lower by 2 is also the same as upper or lower. Now what happens if v is equal to the middle element? Well, then we stop and return the index of the middle element. Otherwise, if v is less than the middle element, we are going to change upper to middle minus 1. So lower will continue to point here and upper will point to a value or the element to the left of lower. Now this of course is outside the boundary of our subproblem. And the way we're going to detect that is that the value of upper will become less than the value of lower. Lower will always be less than or equal to upper in the algorithm, and the moment lower becomes greater than upper, as in this case, we know that it's time to terminate. We know that we have not found v anywhere in the array, and it's time to flag that v is not present in the array. Likewise, if v happened to be greater than the value of the middle element, then we would have changed lower to middle plus 1. So in that case, upper would have continued to point here and lower would have pointed to the next element, which is again outside the boundary of our subproblem. So again, lower would have had a value greater than upper. So we can use lower greater than upper as the time to terminate our while loop. So the while loop is going to continue executing only as long as lower is less than or equal to upper. So lower and upper are going to start off by being 1 and n respectively, and then lower is going to move to the left, lower is going to move to the right, upper is going to move to the left, until both are pointing to the same element when the size of the subproblem is reduced to 1. Right? So the size of the subproblem is delimited by the range from lower to upper. And once we have figured that, once we are down to a subproblem of size 1 and we find that the value v is not equal to the value of that element, then lower will end up exceeding upper, and that's the time to terminate. So if we terminate the while loop without returning in the middle, we know that v is not found in the input sequence, and so we return not found. So this is the binary search algorithm. You can verify that the index of the middle element here is going to be this. For example, if n is equal to 15, that is, if there are 15 elements in the input sequence, then 1 plus 15 by 2 is going to be 16 by 2 or 8. So the index of the middle element is going to be 8. So there will be 7 elements to the left of the middle element. There will be 7 elements to the right of the middle element. So that works well here. If the array had a size of 16, then 1 plus 16 by 2 would have been some fraction. So it would be 1 plus 16 by 2 or 17 by 2, which is 8.5. So 8.5 is clearly not a valid index value. We need to either round it down or round it up. And in this case, we are rounding it up. So middle will be equal to 9. So there will be 8 elements to the left of the middle element and 7 elements to the right of the middle element. This is when the array has a size of 16. This is when the array has a size of 15. So you can see that whether the array length is odd or even, defining middle to be equal to the ceiling of lower plus upper by 2 works well in dividing the array into 2 halves. And if you're going to do the running time analysis of this algorithm, we need to use the fact that after every iteration, we are omitting at least half the elements from further consideration. So we're going to end up with either the left half or the right half. So the number of elements in the next iteration that we are focusing on will be at most half of the number of elements that were there in the previous iteration. It could be actually one less than n by 2 because you can see here that this half of the array has 7 elements, not 8. The total number of elements are 16. So in one comparison, we are down from 16 to 7. So slightly less than half. If our subproblem becomes this subarray, then we'll be down from 16 to 8. In this case, we'll be down to exactly half of the size of the previous subproblem. So half of the size of the previous subproblem is really it's really an upper bound or an approximate uh, value of the subproblem in the next step. It could actually be one less than n by 2. So let's do the running time analysis more formally. If our worst case running time on a problem of size n is t of n, then we can write t of n as the time it takes to solve a problem of size n by 2, which is t of n by 2, plus the time it took for us to make the comparison with the middle element and to discern that we had to focus on either the left half or the right half of the original array. So C here is the time it takes for us to compare V with the middle element and accordingly update lower or upper to point to their next values, to point to appropriate values so that we are focusing on the next subproblem or the next subarray of half the size. And once we do that, then the time it's going to take to work on that subproblem of half the size is going to be t of n by 2. So the running time can be written as t of n is equal to t of n by 2 plus c. So we can solve this recurrence using the recursion tree method, where we first write t of n by itself and then we replace t of n by the right hand side, but then we write the right hand side as c with t of n by 2 as the left child. There's only one subproblem here. If you recall, we use the recursion tree method to solve the recurrence for the merge sort algorithm, and there we had two subproblems of half the size. So we had a left child as well as a right child. And then we continued to recursively replace the running times here by the suitable expressions given by the right hand side of this recurrence. Again, putting the constants over here and writing the subproblems as the left child or the right child, expressing the running time of the subproblem as the left child or the right child of the original node. So in the next iteration, this is going to become C followed by another C followed by t of n by 4. Because t of n by 2 is going to be t of n by 4 plus C. So we can replace t of n by 2 by t of n by 4 and C written in this way. In the next iteration, we'll replace t of n by 4 by t of n by 8 plus C. So this will be C, 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 t of n by 8. So t of n by 4 is going to be replaced by t of n by 8 plus C. And in each step, the value of t of n is going to be the sum of the values of all these nodes. So it's C plus t of n by 2. Alternately, it can be written as C plus t of n by 4, or it can be written as C plus t of n by 8, and so on. And we're going to keep doing this until we end up with only constants in the tree. So we're going to hit the base case where we have only one element in the subproblem. And let's say that t of 1 is some constant k. So how many c's will be there? So there'll be c's all the way down here except in the very last step where we'll have t of 1. By the way, we could have got this by simply opening up this equation further and further. We didn't have to depict it in the form of a tree. We could have just said t of n by 2 is t of n by 4 plus c plus c. This is t of n by 8 plus c plus c plus c and so on down till t of 1 plus a bunch of c's. Now how many c's are going to be here? Well, if we are reducing the size of the problem by a factor of 2 in each step, after one iteration we went down from a problem of size n to a problem of size n by 2. Then we went down to a problem of size n by 4. So after I iterations, we are going to go down to a problem of size n by 2 to the power I. And the number of iterations is going to take us to end up with a subproblem of size 1 will be some value I such that n by 2 to the power I is 1. So when n by 2 to the power I becomes equal to 1, we have bottomed out our recursion. That means at a value of I equal to log of n base 2, right? N is equal to 2 to the power I. So taking log base 2 of both sides, we get I is equal to log of n base 2. After log n iterations, we are going to bottom out our recursion. So this will be, the number of c's here will be approximately log of n base 2. And so we can write the running time t of n as some constant k plus c times log of n base 2, which is basically theta of log n, or just theta of log n. The base 2 is understood. So you can see that by sorting the original sequence, we have brought down the worst case running time from theta of n in linear search to theta of n by theta of log n for binary search. So sorting enables us to solve the searching problem more efficiently. And binary search is a very popular algorithm and a very basic algorithm, and you need to be familiar with it pretty well to be able to use it on an, we're going to use binary search throughout this course. Binary search will be one of the steps of larger algorithms that will use it to solve other kinds of problems.